All right, we have two problems left to go, and here's our second to last one. I have sort of a miniature steamroller. You've probably seen these things that are working on streets and whatnot. So it's a tandem drum roller. So the frame of this thing is at 4,000 pounds. We've got two rollers here, 1,500 pounds each. Roller radius here, it'll be 1.5 feet. The radius of gyration for each of these rollers is 1.25 foot, so we can be using mass moment of inertia there. And so what we're told is this. So here, if you look at it, this is the front. The rear roller has a torque applied to it, so which is going to drive this thing to go forward of 300 foot-pounds. Okay. It rolls without slipping, starts from rest. And so the problem says, find the velocity of this overall system at 10 seconds. So we have start from rest, find the final velocity, and we have a time factor. This is screaming at us momentum. All right. This is a problem where we very much need to do a free body diagram. And so we basically have three masses here. The rear roller, the frame, the front roller. If we just look at the frame, so we have, I'll take the wheels away, and so as the rear wheel drives forward, it kind of pushes this thing ahead, so I have CX going here to the right. Obviously, the roller provides support for the frame. On the front, so the drive comes from the back, the front will be ejecting, so I put DX pushing back against it, and the roller obviously supports the frame again, and here's 4,000 pounds for the weight, which is somewhere in the middle. All right, now I'll note that I picked these to be one forward, one back. If you took them both forward, it wouldn't be a problem. The signs will work out as long as you're consistent, so that's not really an important issue. All right, so we go back. I'll go back to the rear wheel. So here's the rear wheel. So I picked CX to be driving the truck, which it would do. The moment I picked that one to the right, that means this one go to the left. If I've had that one going to this way, this one would have to flip out. These must complement each other and be equal and opposite. It's a free choice, but only on one of them. Then the other one is determined. This went up, that meant CY had to go down. All right. These rollers also have weight, 1,500 pounds coming down through the center. Here's the torque that's driving the thing. So if you think about that, so this is driving this wheel like that. So as this is trying to go through, friction will be ejecting and push that way. And here's the normal force. This should be A. There we go. So, force coming down, there'll be a normal force from the road pushing back up. Going to the front wheel, same basic idea. If dy supports the frame, then the frame pushes down here. 1,500 pounds for the roller. I have dx going to the left, that means it goes to the right over here. And so there's nothing driving this wheel. What will drive it, make it roll? Friction will be the drive to make it go around and around and around. And here's the normal force. All right. Both of these have the same weight, same sizes, so they have the same, their mass moment of inertia is about their centers here and there would be the same. So it's simply mk squared. We were given the radius of gyration, so here we have mass, 1,500 on 32.2 times 1.25, the radius of gyration squared, and boom, we have our mass moment of inertia. Okay. So let's start attacking this problem. Okay, looks like we can roughly see everything. So this is telling me I want to use momentum. The fact that I have these things rotating here, so these now I've isolated this from everything else, so I do not have to apply angular momentum here at the moment. It's not, I've broken the connection and put forces in. So I'm going to look at this, it's rotating, I'm going to do angular momentum here, angular momentum there. And now I would note that if I looked at this center, I could look at the center at the linear momentum, and so how that's moving forward. But that won't get me very far. It makes a lot more sense in both of these to look at angular momentum. Why? Well, the fact that it's rotating is a good reason. The moment that's applied that drives the thing forward, so that's a huge piece of information, is rotating. And also, if I if I look at A here, what is A? It's the instant center, so I'm rotating about A instantaneously. So if I was to take angular momentum at A, well, then we're going to go the initial angular momentum plus the sum of all the external moments equals the final. Okay, well, if I go here, what are the moments relative to A? Well, I've just wiped out NA and FA because I don't know a lot about them. So that's really helpful. So it makes a lot of sense to do angular momentum at A, and for the same reasons, do it at B over here. So that's what we'll do. All right. So we go over here. Let's get all that in. I'll just move that. All right. Move that out. Okay. So starts from rest. Initial angular momentum would be 0. What are the moments applied to A? Well, relative to this whole thing, I have an M here that's applying a clockwise moment. That makes that negative. It's applied for 10 seconds. So I have minus 300 times 10. All right. CX, I have that coming this way. So relative to A, that would be going counterclockwise. That makes that positive. It's 1.5 feet away from here. And I think I have. So we have, that's 1.5 feet. That didn't show up so good. And it's applied for 10 seconds. All right. So now we move on to the angular momentum that results from applying this angular impulse. So we have, so we would have I omega. So here is the angular, mass moment of inertia, which we computed here for the center here at C. All right, omega. All right, omega is very apparently going to be going clockwise. All right, but I really don't need omega. What I'm looking for is the velocity of the overall system. So here at point C, that's really what I want. So rather than put omega in here, I'll have VC divided by R, which is 0.5. Let's say, and that's what I have there. And you'll note the negative because omega will be clockwise. All right. And then, as always, if you're not doing angular momentum at G, then you have to have a term R from A to C cross mass times VC. Okay, so if you use your right hand, go up and turn, that's a negative. So here's mass, here's R is 1.5, and VC. All right, we're assuming VC is going to be going in the positive direction across here. All right, now in doing that, I note that VC equals velocity D equals the velocity of the rig. All right, so I'm looking for the velocity of the system, the rig, what have you. I'm just going to track the term VC all the way through because I'm at C now. VC will apply here. VC will apply there. Okay? All right. So then I go and do the same thing at B. All right? So if you go through this, we have a couple of unknowns. We have the VC unknown and the CX unknown. So we have one equation, two unknowns. Here I get, I'm going to have another equation. So I'm going to add a third unknown here. So here at B, it's the exact same idea. Initial angular momentum is 0. If you look at D relative to B, that's a clockwise moment, so minus dx times 10 times 1.5 equals I omega. Again, we're going to convert omega into V over R. Omega will be clockwise, so there's a negative there. And then we would have, since this is not the center of mass, we're going to have an R from here to the center of mass, cross mass times the velocity of the center of mass. And that's this right here. And again, if you do your right hand rule and check here, that was my left hand, this will be going down. And so we have our negative. All right, so we have two equations, three unknowns. We need a third equation to pop up here. So where are we going to get that? Well, we're going to apply linear momentum to the rig. All right, so what do we have? Initially, when this starts, rig, the initial state at C, the velocity will be 0. Then we're going to apply forces and integrate them. Okay, so I have Cx, if I look over here, going forward, so times 10 seconds. Dx was going backwards, minus dx times 10 equals mass. The rig is 4,000 pounds divided by 32.2 to get our slugs. And here's VC in the second state. That gives me three equations, three unknowns. And you can just very simply solve. And you'll get 7.09 feet per second. And this problem is knocked out.